So I'm going to talk a little bit about the local positioning system, yeah, a little bit from a technical point of view. The local positioning system is an ultra-wideband based system. So we use radio to figure out where the crazy fly is. And first, a little bit of a background. Back in 2015, this was pretty much when the Crazy Fly 2, it was pretty new. We had this dream of creating some sort of affordable positioning system that could be cheap and that people could use at home. We tried all sorts of things. We used web cameras and ultrasound and all sorts of things that we tried out with, I would say, sometimes slightly successful, sometimes not. But then the Decawave DW1000 chip appeared, and Anoa started to play with this. So we made the Loco deck and the Loco node, and started to work on some sort of software for this. And at the same time, there was a guy called Mike Hammer that was doing his PhD at ETH in Zurich, I think, and he was also working on the same type of problems. So we had a collaboration, and a lot of the code, like the base of the Loco code, was contributed by Mike. So this was a very good base to work from, and then we have obviously continued and improved stuff over time. But that was an important contribution. And the first stable version was released in 2017, so that's a few years ago. At that time, we had two-way ranging and TDOA 2. Two-way ranging is that's mainly for flying one crazy fly. It's sort of very robust and easy to use. And TDOA 2 is for flying more than one crazy fly. Then in 2018, we added TDOA 3, which was intended to be actually to replace TDOA 2. TDOA 2 is still there, but TDOA 3 is more robust and flexible and easy to use, I would say. And recently, last summer, we added the long range mode to enable larger systems for TDOA 3. We're going to talk a bit more about that later. So what is a local positioning system? Well, a good way to see this is that it's like GPS, but indoors. And it provides absolute positioning support. So that is, you can have a global coordinate system in your room, and the crazy fly will know where in the room it is in this global coordinate system. And we have some other options like the optical flow deck that is a relative positioning system. Then the crazy fly really doesn't know where it is, but it knows sort of how it has moved since it started. So that's some sort of relative knowledge of the position. But the local positioning system is an absolute positioning system. And this is, I mean, it's useful if you want to fly from some specific point to another specific point. For instance, for some sort of autonomous application, or doing a maybe a show or something else where you want to know where you go pretty much. So the local positioning system is based on ultra wideband radios. And So we're going to start to talk a little bit about what ultra wideband radio is. I think it's not a super old standard, but I think it's maybe, I would guess this is like 10 years old-ish. And ultra wideband radio, like the name implies, it's a very wideband radio. And this means that it's spread over many frequencies. Most radios are maybe using narrow bands, which means that they are using few frequencies. But as you can see in the picture below, ultra wideband is sort of low power, but on a very wide frequency band. And the nice feature with this is that when you transfer to the time domain, you get a very high temporal resolution, which means that if we send a packet from one radio to another one, we can very precisely measure when the packet arrives in the receiver. If you have a narrow band radio, this is not possible, because in the time domain, the information is going to be smeared out over a longer period of time. So the idea of the wideband radio is that we very precisely can measure when the packet arrives, which means that we can precisely measure the time it takes for a radio packet to travel from one radio to another one. And this is what gives the potential to use ultra wideband for local positioning. Yes. And ultra wideband, yes, it's radio, so we can measure when the packets arrive, but it's also possible to put data into the packets. So this means that when we send a packet, we can not only know when it arrives, but we can also transfer useful information in the packet. And that information is mainly used for time information. So for instance, when we send a packet, we also include the transmission time in the packet, which means that the receiving radio can know when the packet was sent. The amount of data that fits in these packets is very limited. I think it's in the order of 100 bytes, 128 or something. So it doesn't fit a lot of data, but some. So we use it for time information and position information and some sequence numbers and stuff like this. So now we have a radio where we can measure times very precisely. And the way to use it is, of course, to use the speed of light. So we measure the time it takes for a radio packet to travel from one radio to another one. And since we know it's going to go with the speed of light, we can calculate the distance. Obviously, the time it takes is very short, so we need a very high resolution timer. I think the timers that we have in the system has a resolution of about 6 millimeters if you translate the speed of light to how far the light travels in one tick of the timer. So this is like the highest resolution we possibly can have physically in the system. So the chip or the module we use, that's called the DWM1000, it contains an ultra wideband radio and an antenna and a very precise timer. So this is like a silicon package that we use in the products. So there is one timer in each of these modules. So that's one timer in each anchor, there's one timer on the local deck, on the Crazy Fly, and so on. And these timers are, like I said, very precise, but they do not run exactly at the same speed, because there is some sort of crystal or whatever it might be that is driving the clock. So this is a bit of a problem, that and this is one of the things that needs to be handled in the system, that all these clocks are running at different speeds. To make it slightly more complex, they also change the speed over time, because the chip becomes warm, for instance, and then the speed changes a bit. So this is something that we handle, and that we're going to talk a little bit more about later on. Okay, we're going to start to talk about the two-way ranging mode. In two-way ranging, the idea is to measure the absolute distance from the Crazy Fly to the anchors, one anchor at a time. And the result is pretty much the distance in meters to each anchor. And when you have the distance to a bunch of anchors, it's pretty easy to estimate the position, obviously, like the 2D picture shows. In this mode, the Crazy Fly is sending a packet to the anchor, and the anchor responds, and there's a little bit of ping pong going back and forth. But since the Crazy Fly is transmitting, there is a limitation of how many Crazy Flies that we can position at the same time, and the limitation is 1. Because if we had 2 Crazy Flies, there would be collisions in the air, and the packets would be lost, and there would be all sorts of complications. So in two-way ranging, we only support 1 Crazy Fly. Yes, and we measure the distance to the anchors. The other sort of a factor that is required is to know where the anchors are located as well, and this is something that's typically measured manually. And this data is stored in the anchor and transmitted to the Crazy Fly in the ultra-wideband packets. So when the Crazy Fly has the distance to anchors and it has the position of the anchors, we push all this information into an extended Kalman filter to estimate the position. It could be done in different ways as well, but the Kalman filter is used for all sensors, all positioning sensors I have pretty much. So this is just one of many ways of estimating position. So let's look at how the sort of packet transmissions, what kind of packets we send and why. So in this graph, we have time is flowing to the right. We have 2 devices. This is probably a Crazy Fly and an anchor. And the idea is pretty much that the device 1 sends a packet, and after a while it's received by device 2. And what we want to know is the time of flight. So how long time it takes for the packet to go from device 1 to device 2, and then we can use the speed of light to calculate the distance. And this would obviously be very easy if we had a shared clock, because then we could just send the packet from device 1. We put the timestamp in the packet, so when it arrives at device 2, it checks with its own clock what time it is and compares that to the time that was transmitted in the packet and get the time difference. Now the problem is that the clocks did not start at the same time, and there is no easy way of synchronizing the clocks either, so we will not really know how long time the time of flight was. So this is not the way that works. So if we want to sort of take the next step, and then like a basic idea is that, yeah, we don't know exactly when the clock started, but if we use time deltas from the same clock, so maybe we look at the time from T1 to T4, then we have the same clock, and the delta is going to be fine. The delta T1 to T4 is going to be fine to compare to delta T2 to T3. So this is an improvement, and it's going to solve some problems, but we still have the issue of that clocks in device 1 and 2 are running at different speeds. They're going to be pretty close, but not close enough. So this is not a complete solution. We also need some way of figuring out how fast the clocks are running. So this is done by assuming that the clock in device 1 and the clock in the device 2 are running at constant speeds, but with some sort of multiplication factor that describes the difference in speed. And the easiest way to measure this multiplication factor, alpha, that I call it here, is to find two places where packets are sent from device 1 to device 2. That's the green arrows in this case. And device 2 will know T1 and T5, and it will know T2 and T6. And here T1 and T5 is measured in the device 1 clock, while T2 and T6 are measured in the device 2 clock. But if we assume that the crazy fly has not moved here, then we know that the time of flight is going to be the same for both packets. So what we can do is simply to take the time delta T1 to T5 and divide it by the time delta T2 to T6. And that's going to give us the alpha. So the assumption here is that the crazy fly moves very slowly compared to the time scale that the packets are transmitted. Like the time between T1 and T5 should not be too long, but it's in the order of milliseconds. So the crazy fly does not if it flies with like 1 meter per second, it's going to be maybe move a few millimeters. So that's fine. We also assume that the clocks are not drifting. The frequency on the clocks are not changing in this time interval. They're going to change over time, but it's a fairly slow process. So within a few milliseconds, they will not change the frequency. So now we know the relation of frequencies for the clocks in the two devices, the alpha. And now it's possible to calculate the time of flight. So for instance, the time T1 to T4, that is, the crazy fly sends a packet, and after a while, another packet is sent back. So this is when we receive, T4 is when we receive this second packet. T1 to T4, that should be exactly the same thing as T2 to T3 plus time of flight back and forth. And then we have to compensate for the difference in clock speed with the alpha. And this makes it possible to solve for the time of flight. And this is pretty much what we do. I don't know if you read maybe the manual for the Decawave ship, the formula is going to look slightly different, but that's because they take the alpha and sort of reorganizes the numbers a bit, but it should be the same. And if we look at this, like the real world scenario, we have the crazy fly, we have one anchor. Then we can see that Crazefly initiates a ranging sequence by sending a packet to the anchor. The anchor responds, and then the Crazefly sends a second packet. And at this time, it would be possible to calculate the distance, but we want the distance. We want to use the distance in the Crazefly and not in the anchor. So that's why we send a fourth packet back to the Crazefly. So at this time, when this is received, the Crazefly can know the distance to the anchor, and it also knows the anchor position, since this was included in the packet. So all is good. We can now push the distance, and we can push the position into the Kalman filter, and hopefully it's going to converge into a nice and stable position. Yes, this is two-way ranging. It's fairly straightforward, I think. The nice thing with two-way ranging is that it's very robust. It's driven by the Crazefly. The Crazefly ranges to one anchor at a time, pretty much round robin. So it does anchor 0, 1, 2, 3, 4, and so on. And since we get the distance to the anchors, it's geometrically very stable as well. You can even fly outside of sort of the space that is covered by the anchors, and that still works very well. But again, the drawback is that it only supports one Crazefly. So if someone would like to fly a swarm or more than one Crazefly, that's then the solution is the time difference of arrival method. When we have two different implementations, but the discussion here is going to be generic, and it's sort of, it holds for both of them. And in TDOA, the idea is to measure the difference in distance to two anchors. This is actually the way that GPS works as well. And it might seem weird to measure the distance and difference in distance, but the nice feature is that it's possible to do this with only anchors transmitting. So the Crazefly does not have to transmit at all. The Crazefly is only listening to the traffic that goes through the air. And this means that we can add as many Crazeflies as we like. I mean, you can compare this to a GPS receiver that is only listening. We can have infinite numbers of phones getting their position. So similar thing here. Again, we push this information into the Kalman filter for estimation. TDOA is nice because we can support many Crazeflies. The drawback is that it is slightly less robust compared to arranging in terms of geometry. And the reason is that it's, if you look at this picture here, it's intended to show that the yellow line, for instance, that is all the possible positions that the Crazefly could have if you're looking at the anchor pair A0 to A2. So the yellow line it has the same difference in distance to A0 and A2. And similar, the green one is for the anchor pair A1 to A2, and the blue one is for the anchor pair A0 to A1. And when the Crazefly is sort of in the center of the system, this is pretty fine. But if we start to get close to the edges or even outside of this space, the geometry becomes less favorable, and it's going to be errors in measurements are going to have a sort of big effect on the estimated position. So for TDOA, it's less robust, but it works very well, like in the flying space that is sort of spanned by the anchors. So let's look at how TDOA works. So like I said, we need a pair of anchors. So we have anchor 1 and we have anchor 2, and we have a crazy fly. And the sort of most simplistic approach would be to let the two anchors transmit at the same time, like is shown in this diagram. And then the packets arrive in the crazy fly some time later, depending on how far away they are from the anchor. And we can record the time that they are received, and we could measure the difference between T2 and T1, and that would give us the difference in distance to the anchors. Again, the clocks are not synchronized, so this is not it will not be possible in reality. And it would also be complex, because if the crazy fly is, for instance, in exactly at the same distance to anchor 1 and 2, there would be a collision of anchors in the receiver, and we would lose them both. So that would be a bad setup. So what can we do to solve this? Well, the idea is to first let anchor 1 transmit, and then sometime later we let anchor 2 transmit. If we just know the time between the transmissions, the one called TX21 here, if we know this time, then the crazy fly could just remove that from the time between T1 and T2, and then it would still have the time difference of arrival. Now again, in this picture, I completely ignore the problems of clocks running at different speeds, but the basic idea is to somehow figure out the time between transmissions. And to solve this, we simply let anchor 2 listen to anchor 1 as well, not only the crazy fly listening to anchor 1. So that means that anchor 2 will actually know when anchor 1 transmitted. The only slight problem is that there is a time of flight there from anchor 1 to anchor 2. So anchor 2 will know when anchor 1 transmitted, except that it also needs to know how far away anchor 1 is. So the question is, how do we solve this? Well, we already know about two-way ranging, right? So if we let anchor 1 listen to anchor 2 as well, then all the packets that they send, they will actually be a two-way ranging between anchor 1 and 2. So the red arrows here, I don't remember if you I don't know if you remember this sort of the picture of the 3 arrows go back and forth. This was exactly what we did in the two-way ranging. So by letting anchor 1 and 2 listening to each other, and they transmit regularly, they will know the time of flight to the other anchor. So that's easy. And as a byproduct or side effect, the crazy fly will be able to will listen to the same packets and will be able to calculate the TDOA between the two anchors. So this is sort of an interesting feature of TDOA, that it is actually two-way ranging between anchors, where the TDOA feature that the crazy fly uses is sort of a side effect. So in this picture, we can see the packets that the crazy fly receives, and we can also see, like, we have the green pair. This will enable the crazy fly to calculate the clock, the alpha 2, and the blue arrows will enable the Crazyflie to calculate alpha 1. That means that it can also recover the clocks from both anchors, which is needed to calculate the TDOA. The time of flight between anchors is also included in the packets that are transmitted. So the Crazyflie gets the time of flight between anchors from the anchors. It might be no. I thought I might have another slide with this. So here we are. The Crazyflie gets all the information it needs. It has time of flight between anchors. It has all the transmission and receive times are included in the packets as well. It knows about the clock frequencies in all the anchors. So, and the positions, they are also included in the packets like we did for two-way ranging. So this is going to be enough for the Crazyflie to calculate the time difference of arrival. And this is pushed into the Kalman filter for estimation. Yes. Again, if you read the documentation for the radio chip, there is probably some sort of a nice formula telling you how to do this. In our implementation, we have separated clock recovery and the two-way ranging between anchors and the TDOA process because they are pretty independent. So we have one piece of code that is keeping track of clocks, and then this is used by the TDOA code and so on. So it makes it the formulas looks or the equations looks different, but they are essentially the same in the end. It's just an easier way of doing it in software. I have mentioned the TDOA 2 and the TDOA 3. TDOA 2 was the first version we did, and that's limited to 8 anchors, and the anchors are transmitting in a fixed time sequence in time slots, synchronized to anchor 0. And this was sort of the easiest way to do it to get started. The drawback is that it's limited. It's no way you can make the system larger or add more anchors, and it's also very, very non-robust. So if anchor 0 dies, the full system dies. So in TDOA 3, we tried to fix this, and we changed to a paradigm where we transmit at random times instead. So the anchors are pretty much all anchors. They're just randomly transmitting data. But this makes it very much more robust because all the anchors are equal, so you can add and remove anchors dynamically. It supports up to 255 anchors. Yeah, generally it's much better, I think. The accuracy is, I think, the same. So if you are choosing between TDOA 2 and 3, I would choose TDOA 3. Yes. Now a little bit about the long range mode that was added recently. In the original flavor of the system, the maximum range of an anchor is around maybe 10 meters. And that's fine. I mean, you can add a lot of anchors, but if you want to cover a big space, this might be possible or tricky to have anchors everywhere, pretty much. Suppose you want to cover 40 by 40 meters, you're going to need to have some anchors in the middle of the floor, for instance. And if that might not be possible in all cases. So we wanted to increase the range of the anchors a bit. And the solution is basically that we have lowered the bit rate of the radio, which makes it reach longer pretty much. This is only supported in TDOA 3, but I mean the solution is pretty straightforward. The problem that occurred was that the timing in the system changes because the packets it takes a longer time to transmit the packets because they are using a lower bit rate. And there is a piece of code called the outlier filter in the system that's trying to remove bad data packets that might have been bouncing around a bit too much, or they for some reason the data is bad. And the outlier filter was very much written for an 8 anchor system with the old bit rate, and there were a bunch of different assumptions. So we did this experiment at the end of last year when we set up a really big system, and we quickly realized that the outlier filter was a problem. But it has been rewritten now, and it's a simplified version where it's also based on the noise level that is configured in the system. There is a setting where you can tell the system what the standard deviation of your ultra wideband data is, the measurements. So it tells the system how noisy the setup is pretty much. The default values are usually good. But these are also used now to configure the outlier filter. So it becomes a little bit more forgiving if the system is noisy, and a little bit more strict if the system is less noisy. The basic idea of this outlier filter is pretty much that we accept measurements that are close to where we think we are. And measurements that seems to be far away are discarded. But if we get a lot of measurements that are outside of this accepted range, we think that maybe we have lost the position, and so then we open up a bit and let more measurements through to let the Kalman filter converge back into a proper position. Yes, let's see what other slides I have. Yeah, I mentioned the Kalman estimator, that we use that for estimating the position for when we have the local system. I just wanted to mention as well that it's used for all positioning. So also if you have an optical flow deck or Z ranger or a lighthouse system, all data is pushed into the same Kalman filter. And this is sort of a nice feature because you can easily use multiple positioning methods at the same time, and you can seamlessly move from say a lighthouse system into a local system as long as they share the coordinate system. It works fine. So I think this is a nice feature. We have a demo that we did a couple of years ago where we switch between, I think, lighthouse, loco, flow. I think that's the ones. If you want to check it out, it's on YouTube. A little bit about possible future work. I mentioned that in TDOA, the anchors are doing two-way ranging, right? And the TDOA part is like a side effect. Since TDOA 3 is completely based on randomness, it's possible to let the crazy fly do some transmissions as well. We usually call this the hybrid mode. We have not, there are some experimental implementations, but not a final and real one. But this is something that could be interesting to do at some point. This would enable crazy flies to do inter-drone ranging and mix it or combine it with ranging to absolute positions, like absolute positioned anchors, for instance. So you could have a mix where the crazy fly chooses to sometimes transmit its position or not. Another thing that could be interesting to look at in the future is antenna delay correction. So when the radio waves arrive at the ultra-wideband radio, there's a long delay when they pretty much pass through the antenna into the physical radio. And this is compensated for. I mean, that's not the problem. The problem is that the delay is slightly different depending on the orientation of the antenna. So this means that if the crazy fly is yawing, for instance, then the delay to the anchors will change slightly. That means that the measured distance is changing a bit, and it can change quite a lot. It's like in the order of maybe 30, 40, 50 centimeters, worst case. And this obviously creates errors in the estimated position. It has turned out to be pretty tricky to compensate for this, and I don't think it's possible to do with some sort of simple equation or something. It's the approaches I have seen is to use neural networks or similar methods to estimate these errors. But it would be very good if at least improve it a bit. Another track that we are looking at is improved hardware. So it would be possible maybe to have better antennas instead of the ones that are built into the radio modules. The MCU on the anchors is a pretty old and tired MCU there's not not a lot of power in it. So it would be nice to have anchors with more oomph in the MCU. So these are things that we have been looking at a bit. We'll see what the future will bring. Yes, and just a quick pointer to documentation for the things I've been talking about. You can find most of it in one way or another in the repository documentation for most of it is in the LPS node firmware, but some of it might be in the Crazyflie firmware as well. So yeah, that's all my slides. Do we have any questions?